Right now, as you sit here listening to this, you are inside a structure so large that light itself takes 20,000 years to cross it. It is not the Milky Way. It is not the observable universe. It is just your neighborhood. The Orion Arm is the local spiral arm segment of our galaxy, a ribbon of stars, gas and dust that most people have never heard of, and it contains everything you have ever seen in the night sky. Every constellation, every nebula visible to your naked eye, every star your ancestors used to navigate the oceans. All of it sits inside this one structure, and that structure is so small compared to the rest of the galaxy that on most maps, it barely deserves a label. Tonight, you're going to understand what that means. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Now, let's begin. Let us start with something you already know: the ground under your feet. You are sitting on a ball of rock and iron roughly 8,000 miles across. It is coated in a thin layer of water and wrapped in an even thinner shell of gas that extends only about 60 miles above the surface before it fades into the vacuum of space. That shell of gas is your atmosphere. It is the only thing standing between you and the void of the cosmos. And every city ever built, every ocean ever crossed, every mountain ever climbed, every battlefield and every cathedral, and every place any human being has ever called home exists within that fragile envelope of air clinging to the surface of this planet. If you could see the Earth from far enough away, you would notice something that is easy to forget when you're standing on it. The atmosphere, this life-sustaining layer that contains the entirety of human experience, is thinner relative to the planet than the skin of an apple is relative to the apple. That is how small your world is, even before we leave it. Now let us pull back. The Earth orbits a star. You call it the Sun. It sits roughly 93 million miles away, a distance so large that light itself, the fastest thing in the universe, takes about 8 minutes and 20 seconds to cross it. That distance, Earth to the Sun, is what astronomers use as a basic yardstick for measuring the solar system. They call it 1 astronomical unit, and it feels enormous. 93 million miles is not a number any human being can intuitively grasp. If you could somehow drive a car at highway speed toward the sun, running day and night without stopping, that trip would take you more than 170 years. You would be dead many times over before you got there. Your grandchildren would be dead. The language you spoke when you started might not even be recognizable by the time the car arrived. But here's the thing. In the language of the cosmos, 1 astronomical unit is nothing. It is a rounding error. It is a footnote in a book no one reads. Everything that makes that distance feel enormous is a consequence of how small you are, not how big the distance is. And if 1 astronomical unit is already beyond intuitive human comprehension, then the rest of the solar system will start to feel almost absurd. The solar system extends far, far beyond Earth's orbit. Mars orbits at roughly 1.5 astronomical units from the Sun. Even that relatively short hop, just half an astronomical unit farther out than we are, is a journey that takes our fastest spacecraft about 7 months to complete. Jupiter, the largest planet, orbits at about 5 astronomical units, roughly 484 million miles from the Sun. At highway speed, you would need over 800 years to drive there. Saturn, with its famous ring system, orbits at roughly 9.5 astronomical units. Out beyond Saturn, The solar system grows colder, darker, and lonelier. The Sun, which dominates the sky from Earth, becomes a smaller and dimmer point of light with every orbit you pass. Uranus circles the Sun at about 19 astronomical units. Neptune, the outermost major planet, orbits at approximately 30 astronomical units from the Sun. From Neptune's orbit, the Sun is so far away that it appears as little more than an unusually bright star. You could cover it with the head of a pin held at arm's length. That means the solar system, measured from the Sun to Neptune's orbit, spans a diameter of roughly 60 astronomical units. In miles, that is about 5.5 billion miles from one side to the other. In kilometers, roughly 9 billion. These are not numbers the human brain was built to process. They are abstractions that sound precise but carry no real weight in everyday experience. 5.5 billion miles. The human mind does not naturally process a number like that. To give you a sense of what it means in practical terms, consider the Voyager 2 spacecraft. It launched from Earth on August 20th, 1977. It flew past Jupiter, Saturn, Uranus, and Neptune, conducting flybys of all 4 gas giant planets in what remains one of the most ambitious and elegant missions in the history of space exploration. The trajectory that made this possible, using the gravity of each planet to slingshot the spacecraft toward the next, was a once-in-175-year alignment. Voyager 2 has been traveling at tens of thousands of miles per hour since the day it launched. And it took 12 years. 12 full years of continuous flight at roughly 35,000 miles per hour, just to reach Neptune. That is the scale of the solar system. A spacecraft moving fast enough to cross the entire continental United States in about 5 minutes needed more than a decade to travel from the inner solar system to the outer edge. And yet, for all its vastness, the solar system is microscopic when you measure it in the units that actually matter beyond the Sun's influence. Those units are light years. A light year is the distance that light travels in 1 year, moving at approximately 186,000 miles per second, and not per hour, per second. Light is so fast that it could circle the entire Earth 7.5 times in a single second. It crosses the distance from the Earth to the Moon in about 1.3 seconds. It reaches Mars in as little as 3 minutes when the 2 planets are closest. But even at that velocity, even moving at the fastest speed that anything in the universe can travel, light still needs time to cross large distances. It needs over 5 hours to reach Pluto. It needs a full year to travel 1 light year. Work that speed out over the course of those 365 days, every second of every minute of every hour of every day, and you get a distance of approximately 5.88 trillion miles. That is 1 single light year. And it is the smallest unit astronomers use when talking about the space between stars. Now compare that to the solar system. The entire span from the Sun to Neptune, that 5.5 billion mile expanse that took Voyager 2 12 years to cross, measures less than 1,000th of a single light year. Less than 1,000th. If a light year were a mile, the solar system from Sun to Neptune would be about 5 feet across. Not 5 miles, not 500 feet, not 50 feet, 5 feet. The height of a short person. That is your entire planetary neighborhood, measured against the first meaningful unit of interstellar distance. Everything humanity has ever explored, every planet we have photographed, every moon we have landed on, every ring system and asteroid belt and comet tail we have studied, all of it fits inside 5 feet of a mile-long ruler. The other 5,275 feet are empty space we have barely begun to enter. This is where most people's intuition begins to break. We are conditioned to think of the solar system as huge, and it is huge by every measure that matters to daily human life. But the distances between stars operate on a completely different scale. A scale where everything you have ever known, every planet, every moon, every asteroid, every piece of hardware humanity has ever launched, all of it fits inside a volume so small that it essentially vanishes when you start measuring in light years. The spacecraft that demonstrates this most painfully is Voyager 1. It launched on September 5th, 1977, about 2 weeks after its twin Voyager 2. It carried scientific instruments, cameras, and a golden record, a phonograph disc containing sounds and images from Earth, intended as a message to any intelligence that might someday find the spacecraft drifting through interstellar space. It flew past Jupiter and Saturn, taking some of the most iconic photographs in the history of space exploration. Images that revealed the swirling storms of Jupiter in breathtaking detail and the intricate structure of Saturn's rings. And then, in 1990, from a distance of about 40 astronomical units, Voyager 1 turned its camera back toward Earth one final time and captured the image that Carl Sagan would later call the pale blue dot. In that photograph, Earth appears as a tiny speck of light, less than a single pixel wide, suspended in a beam of scattered sunlight. Everything you have ever loved, everything you have ever feared, every war fought and every child born and every song ever sung, all of it contained in that single pale pixel. And Voyager 1 was not even very far away when it took that picture. 40 astronomical units is still within the solar system, still within the sun's gravitational domain, still, in cosmic terms, right next door. Voyager 1 kept going. It crossed the termination shock, the boundary where the solar wind slows to subsonic speeds, in 2004. It crossed the heliopause, the outer edge of the sun's magnetic influence, in 2012. That crossing was historic. Voyager 1 became the first human-made object to enter interstellar space, the vast region between the stars. Headlines around the world announced that Voyager had left the solar system. And in a certain technical sense, it had. It was beyond the sun's magnetic bubble. But it was not beyond the sun's gravitational reach. The Oort cloud, a theoretical shell of icy bodies surrounding the solar system, may extend as far as 1 or even 2 light years from the sun. Voyager 1 will not clear the Oort cloud for tens of thousands of years. It has left the sun's magnetic domain, but not its gravitational one. It is in interstellar space, but still, in some sense, inside the solar system's outermost boundary. And here is the number that puts everything into devastating perspective. As of the mid-2020s, after nearly 50 years of continuous flight, after crossing the entire breadth of the solar system's magnetic domain, after becoming the most distant object humanity has ever created, Voyager 1 is roughly 165 astronomical units from the Sun. That sounds impressive. It is genuinely impressive by any engineering standard. No other machine has traveled so far from its makers, but convert that distance to light travel time and the achievement collapses into something else entirely. 165 astronomical units is approximately 23 light hours, less than 1 light day. Voyager 1 has been flying for almost half a century, and it has not yet traveled a distance that light covers in a single day. The nearest star is over 4 light years away. At Voyager 1's current speed of roughly 38,000 miles per hour, It would take approximately 70,000 years to reach that star. 70,000 years. The entire span of recorded human civilization, everything from the first Sumerian clay tablets to the phone or computer you're using right now, covers roughly 5,000 years. Voyager 1 would need more than 14 times the entire length of recorded human history to crawl across the gap to the closest neighboring star. And that neighbor, Proxima Centauri, is by galactic standards sitting in our lap. It is the nearest option we have. Proxima Centauri is a small, dim red dwarf star. It has roughly 12% of the Sun's mass and emits less than 1% of the Sun's light. If you replace the Sun with Proxima Centauri, the Earth would freeze solid almost immediately. It is so faint that you cannot see it with your naked eye even under the darkest skies on Earth, despite being the closest star to our solar system. It is part of a triple star system called Alpha Centauri, which also includes two larger, more sun-like stars designated Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is slightly larger and brighter than the Sun. Alpha Centauri B is slightly smaller and dimmer. Those two orbit each other as a relatively close pair, circling their common center of gravity roughly every 80 years. Proxima Centauri orbits both of them at a much greater distance, so far from the central pair that it takes hundreds of thousands of years to complete a single orbit. Some astronomers have debated whether Proxima is truly gravitationally bound to the other two at all, though current evidence suggests it is. The entire Alpha Centauri system sits approximately 4.24 light-years from Earth. In miles, that is roughly 25 trillion. 25 followed by 12 zeros. If you tried to count to 25 trillion, one number per second, without sleeping, without pausing, it would take you nearly 800,000 years. That is the distance to the nearest star, expressed in miles. 25 trillion miles of functionally empty space separating our solar system from Alpha Centauri. There is almost nothing in that gap. No gas stations, no waypoints, no asteroids worth mentioning, no rogue planets that we have detected. Just vacuum. Cold, dark, silent, and absolute. A void so thorough and so vast that anything crossing it would spend decades surrounded by nothing in every direction. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri. They named it Proxima Centauri b, and it is roughly Earth-sized, orbiting within what might be the habitable zone of its star, the range of distances where liquid water could theoretically exist on a planet's surface. That discovery sent a ripple of excitement through the scientific community and the public alike. The nearest star to the Sun has a potentially habitable world, but reaching it remains an engineering problem so vast that no serious proposal exists for sending a crewed mission within any time frame that matters to the people alive today. 4.24 light years is simply too far with anything resembling current technology. Even the most ambitious theoretical proposals, like Breakthrough Starshot's concept of laser-propelled, microchip-sized probes, would take more than 20 years traveling at 20% of light speed to reach Proxima Centauri, and those probes would carry almost no instrumentation and would scream past the target with no ability to slow down. The nearest star is functionally unreachable for human civilization, and it is the easiest target in the sky. Now, let us expand the picture a step further. Proxima Centauri is not the only star in our general vicinity. There is a small community of stars scattered around the Sun in every direction, and astronomers have mapped it in considerable detail using increasingly precise instruments over the past century. Within about 17 light years of the Sun, there are roughly 60 known stars. The vast majority of them are red dwarfs, a class of star that is small, cool, and profoundly dim. Red dwarfs are actually the most common type of star in the Milky Way, making up roughly 70 to 75% of all stars in the galaxy. But they are so faint that not a single one is visible to the naked eye from Earth, no matter how dark the sky. You could be standing directly under one and never know it was there without a telescope. The few stars in the local neighborhood that are bright enough to see unaided are the exceptions, the overachievers, the rare larger and hotter stars that happen to sit nearby. Sirius, the brightest star visible from Earth, sits about 8.6 light-years away. It is actually a binary system, a hot, luminous main sequence star paired with a tiny white dwarf companion called Sirius B, Barnard's star. One of the nearest individual stars to the Sun at about 6 light-years is a dim red dwarf that moves across the sky faster than any other star, a property called high proper motion that made it a target of intense study throughout the 20th century. Epsilon Eridani, roughly 10.5 light-years away, is a young sun-like star surrounded by a debris disk that resembles an early version of our own solar system, and has long been considered one of the most promising nearby candidates for harboring planets. Wolf 359, a dim red dwarf about 7.9 light-years away, is so faint that despite its proximity, it is completely invisible to the naked eye. Ross 128 sits about 11 light-years from Earth, another quiet red dwarf with a confirmed exoplanet. These are our neighbors, the stars whose light reaches us in less than 2 decades, the stellar equivalent of the houses on your street. And if you mapped all of them out in 3 dimensions, plotted every one of those 60 stars as a point in space, you would see something striking. They are scattered in every direction with no pattern, no structure, no discernible logic. Some sit above the plane of the Milky Way, some below it, some closer to the galactic center, some farther away. There is no grid, no symmetry, no tidy arrangement, just a sparse, random scattering of mostly dim points, separated by vast gulfs of empty space. The local stellar neighborhood is not crowded. It is not dense. It is a handful of tiny objects sprinkled across a volume of space, so large that if you could somehow stand outside it and look in, you would struggle to find the stars at all. They would be lost in the emptiness, invisible against the dark. This is the reality of interstellar space that photographs never capture, and science fiction rarely conveys. Space between the stars is not merely empty. It is overwhelmingly, oppressively, almost perfectly empty. The stars are exceptions. The void is the rule. To feel what the emptiness really means, it helps to build a picture you can hold in your mind. Imagine shrinking the sun down to the size of a small marble, about 1 centimeter across. A glass marble you could hold between your thumb and forefinger. At that scale, the Earth would be a barely visible grain, thinner than a strand of human hair, orbiting about 1 meter away from the marble. Neptune, the outermost planet, would be another tiny speck orbiting roughly 30 meters from the marble. The entire solar system from the Sun to Neptune would fit comfortably inside a large building. Now, at this same scale, where is the nearest star? Think about it for a moment. The solar system fit inside a building. Surely the nearest star must be across the parking lot, maybe across the campus, maybe across town? The answer is roughly 200 miles away. 200 miles of emptiness between two objects smaller than your fingernail. If you place the marble sun on a table in New York, the nearest star would be a speck so small you could barely see it. Smaller than a grain of rice, sitting somewhere near Baltimore. Not a model of Baltimore, not a simulation. Actual Baltimore. 200 actual miles of actual space away. And between them, stretching across the entirety of New Jersey and Pennsylvania and Maryland, there would be nothing. No other stars, no planets, no gas clouds, no light. Just 200 miles of pure, silent void. That is the local neighborhood of the sun. That is what 4.24 light years looks like when you shrink the universe down to something you can almost visualize. And remember, Proxima Centauri is the closest. Barnard's star at this scale would be roughly 300 miles away, somewhere in Virginia. Sirius would be roughly 400 miles away, farther than the distance from New York to Pittsburgh. Every one of those 60 nearest stars sits hundreds of miles from every other one in this model, each one a speck or a grain of sand floating in open air, separated from its neighbors by distances that would take you hours to drive through at highway speed. And all of those specks, every last one of them, are still part of what astronomers call the immediate neighborhood, the local volume, the stars next door. If this local neighborhood already feels immense, if the emptiness between even the nearest stars is already difficult to hold in your mind, then what comes next may feel almost impossible. Because here is something most people never consider. That entire volume, that bubble of roughly 60 stars spread across 34 light years of diameter, as vast and as lonely as it is, represents almost nothing in galactic terms. It is not a significant region of the galaxy. It is not even a significant region of the galaxy's local structure. It is a pinprick. A dot so small that no map of the Milky Way drawn at any reasonable scale could make it visible. You could not point to it. You could not label it. It would vanish into the thickness of a pencil line. And it is sitting inside something else. Something so much larger that the local neighborhood effectively disappears within it, like a single cell inside a living body. Something that stretches for thousands of light years in every direction. Something that contains not just your 60 nearest stellar neighbors, but millions upon millions of stars, entire nebulae visible across the galaxy, colossal clouds of molecular gas and dust, star-forming regions where new solar systems are being assembled right now as you listen to this, and structures so enormous that light itself takes thousands of years to cross them. You have been living inside this structure since the day you were born. Every human being who has ever existed has lived inside it. Every star you have ever seen with your naked eye on a clear night belongs to it. Every constellation your ancestors named, every bright point of light that ancient navigators use to cross the oceans, every nebula visible from Earth without a telescope, all of it sits within this one feature of the galaxy. And almost nobody knows its name. It is not the Milky Way, although it is part of the Milky Way. It is not a galaxy or a nebula or a star cluster. It is something most people never learn about in school and never encounter in casual conversation about space. It is a structural component of the galaxy itself, a segment of spiral arm, a ribbon of stars and gas and dust winding through the galactic disk between two of the Milky Way's larger spiral arms, curving through space like a river flowing between distant mountain ranges. It is roughly 3,500 light years wide, It extends for at least 20,000 light years from end to end. It contains every star you can see in the night sky with your unaided eyes. It contains the Orion Nebula. It contains some of the most famous and luminous stars in the sky, and it is called the Orion Arm. You are inside it right now. You have always been inside it. There is nowhere else you have ever been. The local stellar neighborhood, that bubble of 60 stars spread across 34 light years that already felt impossibly large, fits within the width of the Orion Arm more than 100 times over. 100 times. That is not a rough estimate. The arm is 3,500 light years wide. The neighborhood is 34 light years across. You could lay the entire local stellar neighborhood end to end across the Orion Arm 100 times and still not reach the other side. If the Orion Arm were a highway stretching to the horizon, the local neighborhood would not be a car on that highway. It would not be a pebble on the shoulder. It would be a mote of dust on a painted line, invisible to anyone passing by. Everything you thought was large is about to become small. The solar system, less than 1,000th of a light year across, is a speck inside the local neighborhood. The local neighborhood, 34 light years across, is a speck inside the Orion Arm. And the Orion Arm itself, this structure stretching at least 20,000 light years through the galactic disk, a structure so large that light launched from one end at the moment the last ice age began on Earth, still would not have reached the other end, is not even one of the galaxy's major features. Not even one of its primary arms. For decades, astronomers didn't even consider it a real spiral arm. They called it a spur, a minor bridge, an afterthought between the structures that actually mattered. They were wrong about that, as it turns out. But what the Orion Arm truly is, how it was discovered, why its classification has changed, and why its real scale changes everything you think you understand about your place in this galaxy, is the story we are about to tell. The word locale is about to stop meaning what you think it means, and the camera is pulling back. It is not going to stop for a long time. To understand what the Orion Arm is, you first need to understand the thing it belongs to. You need to see the Milky Way. Not the way you see it from Earth, not the way it appears on a clear summer night, as a band of hazy light smeared across the darkness, but the way it actually is. A structure, a machine, a physical object with a shape and a size and a geometry that took centuries of painstaking effort to figure out. Here is the problem. You are inside the Milky Way. You have always been inside it. There is no window you can look through to see the whole thing from outside. Every star you observe, every nebula you photograph, every measurement you take, all of it is gathered from a single vantage point deep within the disk of the galaxy. Trying to map the Milky Way from inside is like standing in the middle of a dense forest and trying to draw an accurate map of the entire forest based only on what you can see through the trees in every direction. You can measure the distances to individual trees, you can figure out roughly how dense the forest is in one direction versus another. But the overall shape, the boundary, the structure, all of that has to be inferred. You cannot simply step outside and look. And yet, over the course of centuries, astronomers did exactly that. They inferred it. Through careful observation, through radio surveys that could penetrate the dust that blocks visible light, through infrared telescopes that revealed structures hidden behind curtains of gas, and most recently, through the extraordinary precision of space-based observatories like the European Space Agency's Gaia mission, which has measured the positions and motions of nearly 2 billion individual stars, astronomers have assembled a picture of the galaxy we live in. It is not a complete picture. There are still gaps, still uncertainties, still active debates about the details. But the broad strokes are known, and they are magnificent. The Milky Way is a barred spiral galaxy. It is a flat disk of stars, gas, and dust, roughly 100,000 light years in diameter, and about 1,000 to 2,000 light years thick in most places. Though much thicker at the center, where a bulge of older stars swells to perhaps 10,000 light years across. 100,000 light years. Let that number settle for a moment. We established earlier that the distance to the nearest star is 4.24 light years, and that crossing it would take roughly 70,000 years with current technology. The Milky Way is more than 20,000 times that distance across. A beam of light leaving one edge of the galaxy right now would not reach the far edge for another 100,000 years. The galaxy is so large that light, the fastest thing physics allows, needs a geological epoch to traverse it. At the very heart of the galaxy sits a supermassive black hole called Sagittarius A star, with a mass of roughly 4 million times the mass of the Sun. It is surrounded by dense swarms of stars orbiting at tremendous speeds, some of them whipping around the black hole in as little as 16 years. The galaxy contains somewhere between 100 billion and 400 billion stars, depending on how you count the smallest, dimmest red dwarfs that make up the vast majority but contribute very little light. And threaded through the disk of the galaxy, defining its most striking visual feature, are the spiral arms. If you could somehow rise above the Milky Way and look straight down at it, the way you might look at a pinwheel from above, you would see a central bar of stars stretching across the middle, roughly 27,000 light years long, and winding outward from the ends of that bar. A set of curved spiral arms sweeping through the disk like the arms of a slow, enormous whirlpool. These arms are not solid structures. They are not walls of stars rotating in lockstep. They are density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center, the way cars bunch up in a traffic jam even though each car is still moving forward. A star approaching a spiral arm encounters a gravitational compression zone. It slows, it lingers, it participates in the denser region for a time, and then it drifts out the other side as the arm pattern moves on. The arm persists as a pattern even though the individual stars that make it up are constantly changing. The spiral structure you see in photographs of other galaxies is not a fixed arrangement. It is a standing wave, a persistent pattern moving through a sea of orbiting stars. The Milky Way has two major spiral arms, based on observations from NASA's Spitzer Space Telescope in the mid-2000s, which surveyed the galaxy in infrared light and could see through the dust that obscures so much invisible wavelengths. The two dominant arms are the Perseus arm and the Scutum Centaurus arm. These are the galaxy's primary features, the longest and most prominent spiral structures, wrapping around the disk for tens of thousands of light years. Between and around these major arms are several smaller, less prominent structures. The Sagittarius arm, once considered a major arm, is now classified as a minor one. The Norma arm sits closer to the galactic center, and between the Sagittarius arm and the Perseus arm, roughly 2/3 of the way out from the center of the galaxy, there is a structure that, for most of the history of modern astronomy, was considered barely worth mentioning. It was called the Orion Spur, or the local spur. a small, minor bridge of stars and gas connecting the two larger arms on either side, the way a footpath might connect two major highways. It was mapped, labeled, and then largely ignored by researchers focused on the grander structures of the galaxy. It appeared on diagrams as a short, stubby feature, sometimes drawn with a dashed line to emphasize its insignificance. It was not considered a real arm. It was a spur, a footnote, a minor wrinkle in the fabric of the galaxy. And the sun was inside it. Earth was inside it. Every human being who had ever lived was inside it. But it did not matter much to galactic astronomers, because the Orion spur was small and unimportant compared with the great sweeping arms that define the galaxy's structure. That assessment turned out to be wrong, significantly wrong. But before we get to why, we need to understand what this structure actually is in physical terms. Because naming something is not the same as knowing it. And the Orion Arm deserves to be known properly. The Orion Arm, to use its current and more accurate name, is a spiral arm structure located between the Sagittarius Arm on the side closer to the Galactic center and the Perseus Arm on the side farther from the center. It is approximately 3,500 light-years wide, measured perpendicular to its long axis, and it stretches for at least 20,000 light-years along its length, curving gently through the disk of the galaxy in the same direction as the major arms. Some recent analyses using data from the Gaia mission suggest it may extend even farther, perhaps 25,000 light-years or more, though the precise boundaries depend on which traces you use to define where the arm begins and ends. It has also been called the Orion Cygnus Arm, the Local Arm, and the Orion Bridge, depending on the era and the astronomer. Each name reflects a different attempt to describe the same feature from slightly different perspectives. The name Orion Arm comes from the constellation Orion, one of the most recognizable patterns in the night sky, visible from virtually everywhere on Earth during the appropriate season. And this is a point worth pausing on, because it is a source of genuine confusion that trips up even people who follow astronomy casually. The Orion Arm is not the Orion constellation. Those are two fundamentally different things. The constellation Orion is a pattern of bright stars as seen from Earth. It is a two-dimensional illusion, a set of stars that appear close together on the sky, but are actually at wildly different distances from us. The stars of Orion's belt, for instance, are roughly 800 to 1500 light-years away. Betelgeuse, the red supergiant that marks Orion's shoulder, is approximately 700 light-years from Earth. It is one of the largest stars known, so bloated that if you placed it where the sun is, its outer layers would extend at least past the orbit of Mars, and possibly as far as Jupiter. Rigel, the blue supergiant at Orion's foot, is roughly 860 light-years away, and shines with the luminosity of over 100,000 suns. These stars are not physically close to each other. They are not gravitationally bound. They just happen to lie in roughly the same direction when viewed from our particular location. The constellation is an accident of perspective, nothing more. But many of those stars, the ones that make up the constellation Orion as we see it from here, do happen to lie within the Orion Arm. They are inside the same galactic structure as the Sun. They are part of the same ribbon of stars and gas winding through the disk. And that is why the arm carries the constellation's name. Not because the arm is the constellation, but because some of the most prominent and visually striking stars in that constellation are embedded within this arm segment, And the arm was identified partly by studying those stars and the nebulae surrounding them. The Orion Nebula, one of the brightest and most studied nebulae in the sky, designated M42, sits roughly 1,300 light years from Earth. It's a massive stellar nursery, about 24 light years across, where new stars are being born inside collapsing clouds of gas and dust. And it lies squarely within the Orion Arm. When you look at the Orion Nebula through a telescope, you are looking into your own galactic arm. You are seeing the interior of the structure you are embedded in. Now, let us place the Sun inside this structure with some precision, because where you sit within the Orion Arm matters. The Sun is located on the inner rim of the arm, the side closer to the galactic center, roughly halfway along the arm's length. It is approximately 26,000 light years from the center of the galaxy, which puts it a little more than halfway from the core to the outer edge of the disk. This is not the center of the Milky Way. It is not the edge. It is an unremarkable middle zone, a quiet suburb far from the dense, radiation-soaked chaos of the galactic core, and far from the sparse, thinning outskirts where the disk fades into the halo of ancient globular clusters and dark matter. The Sun does not sit at the center of the Orion Arm either. It sits near one edge, the inner edge, offset from the arm's midline toward the galactic center. And it sits within a particular local feature of the arm's interstellar medium, a relative cavity in the gas and dust called the local bubble, a region of unusually low density space, roughly 1,000 light years across, that was carved out by a series of supernova explosions roughly 14 million years ago. We will explore the local bubble in detail later, but for now, the key point is this. The Sun is not in a random location within the galaxy. It is not floating in some undefined region of the Milky Way. It is embedded within a specific galactic structure, the Orion Arm, at a specific position within that structure, near the inner rim, about halfway along the arm's length, inside a local cavity carved by ancient stellar deaths. You are not just in the Milky Way in some vague, general sense. You are at an address, a precise, measurable, physically real address within a specific arm at a specific distance from the galactic center, surrounded by specific features of the interstellar medium that shape the environment around the Sun in ways that matter for the history of life on Earth. And that address is inside the Orion Arm. This matters because it changes the way you think about what you see in the night sky. Every star visible to your naked eye on a clear, dark night is inside the Orion Arm or very close to it. The farthest naked eye stars are a few thousand light years away at most, with a handful of rare supergiants pushing that envelope. The arm is 3,500 light years wide and 20,000 light years long. Your entire visual sky, every pinpoint of light, every constellation, every asterism, all of it is the interior view of one spiral arm segment seen from within. You are not looking at the galaxy when you look up. You are looking at your arm. The galaxy as a whole, with its 100 billion or more stars and its sweeping spiral architecture, is almost entirely invisible to your unaided eyes because most of it is hidden behind layer upon layer of gas and dust in the galactic disk, scattered across distances so vast that individual stars are far too faint to register on the human retina. The stars you know and recognize, the ones your culture named and your ancestors used to mark the seasons and navigate the oceans, are your immediate galactic neighbors within this one structural feature. The night sky is not a window onto the Milky Way. It is a window onto the Orion Arm, seen from the inside. And until very recently, almost nobody realized that. Now here is where the story takes a turn that matters for the rest of this narrative. For decades, the Orion Arm was treated as a minor feature, a spur, a small secondary structure of little consequence compared with the great spiral arms. This classification was based on the best data available at the time, which suggested that the arm was relatively short and that its density of star-forming regions was significantly lower than the density in the major arms. In 1976, astronomers Yvonne and Yves Georgelin published what became the standard map of the Milky Way's spiral structure. In that map, the local arm was drawn as a spur, a secondary appendage, much shorter and less significant than the Perseus or Sagittarius arms. That classification stuck for decades. Textbooks printed it, diagrams repeated it. The Orion spur became the accepted label. And if you grew up learning about the Milky Way's structure in school, you probably absorbed the idea, perhaps without even noticing, that the sun's home was a minor, unremarkable piece of galactic real estate. Not a real arm, just a spur. But starting in the early 2010s, a series of precise measurements began to challenge the picture. A team led by astronomer Ye Xu at the Chinese Academy of Sciences used the Very Long Baseline Array, a network of 10 radio telescopes spread across the United States, to measure the distances to star-forming regions within and around the Orion Arm with unprecedented accuracy. The technique relied on parallax, the same principle your brain uses to judge distances with two eyes. By observing the same source from different points in Earth's orbit around the Sun, separated by the full diameter of the orbit, they could triangulate extremely precise distances to objects thousands of light years away. They targeted masers, intense natural sources of microwave radiation found in regions where massive stars are forming. Masers are the interstellar equivalent of lasers, producing tightly focused beams of radiation at specific radio frequencies. Because they are so bright at radio wavelengths, they can be observed and measured with extreme precision, even across distances of thousands of light years, making them ideal targets for distance measurement in the dusty, crowded environment of the galactic plane, where visible light observations are often impossible. In 2013, the team published findings showing that the Orion Arm contained more high-mass star-forming regions than previously thought. Several regions that had been assumed to belong to the more distant Perseus Arm turned out, when measured precisely, to be much closer. They were inside the Orion Arm. The arm was not as sparse as the old map suggested. It had more star-forming activity than anyone had credited it with. Then, in 2016, Xu and colleagues published a follow-up study that went further. Using 8 new parallax measurements of masses in and around the arm, combined with all previous data, they showed that the Orion Arm is substantially longer than the old spur classification suggested. Its length extends to at least 20,000 light years. Its pitch angle, the angle at which the arm tilts relative to circles drawn around the galactic center, is between roughly 10 and 12 degrees. And its star formation rate, the rate at which new stars are being born inside it, is comparable to the rates in the galaxy's major spiral arms. This was a significant finding. The pitch angle and star formation rate are two of the key diagnostics astronomers use to distinguish major arms from minor spurs. A spur should have a different pitch angle and a lower rate of star formation than a true arm. The Orion Arm matched the major arms on both counts. The researchers concluded that the Orion Arm should no longer be classified as a spur. It is either an independent arm segment, wrapping less than a quarter of the way around the galaxy but with structural properties comparable to a major arm, or it is a substantial branch of the Perseus Arm that extends inward toward the galactic center. Either way, the old label was wrong. The Orion Arm is not a minor footnote on the galactic map. It is what the researchers described as a fifth major feature of the Milky Way's spiral structure. This reclassification matters not because it changes anything physical. The arm is the same object it always was. The stars inside it did not move. The gas did not rearrange itself. What changed is our understanding of where we live. For decades, the implicit message of the galactic maps was that the sun happened to be located in a minor, insignificant structure, a little spur between the real arms. That was comforting in a way. It made our location seem modest and unimportant, which matched the general Copernican principle that there is nothing special about where we are. But the revised picture is different. The sun is located inside a genuine spiral arm structure, one with active star formation, substantial length, and properties that rival the galaxy's primary arms. We are not in a footnote. We are in a chapter. A long, complex, physically significant chapter of the Milky Way's structure, one that may wrap nearly a quarter of the way around the galaxy. The change also matters because it affects how we think about the scale of our surroundings. When the Orion Arm was dismissed as a spur, it was easy to imagine it as a small, manageable feature, something local in a comfortable sense. But a structure 20,000 light-years long with the star-forming intensity of a major arm is not small in any sense. It is not manageable. It is not something you can cross or map casually. It is a galactic-scale feature that happens to contain us, and recognizing its true size forces a recalibration of what the word local means when applied to our position in the Milky Way. And the scale of that chapter is what makes this story so disorienting. The Orion Arm is 3,500 light-years wide. To feel what that means, step back from the abstract numbers and consider it in terms we have already established. We showed earlier that the nearest star, Proxima Centauri, is 4.24 light-years away, and that reaching it with current technology would take roughly 70,000 years. The width of the Orion Arm is more than 800 times that distance. 800 separate trips to Proxima Centauri, each one 70,000 years long, laid end to end, to cross the arm from one side to the other. The journey to the nearest star, which already seemed impossible, would need to be repeated 800 times in succession just to traverse one dimension of the structure you already live inside. At Voyager 1's speed of roughly 38,000 miles per hour, crossing the width of the Orion Arm would take approximately 60 million years. That is not a human timescale. That is not even a civilizational timescale. That is a geological timescale. It is roughly the amount of time that has passed since the asteroid impact that ended the age of the dinosaurs. The width of the Orion Arm, just its width, not its length, spans a crossing time so enormous that it rivals the entire reign of mammals on this planet from the death of the dinosaurs to the present day. And the arm is not just wide, it is 20,000 light-years long. If crossing its width would take roughly 60 million years at Voyager speed, then traversing its full length would take roughly 350 million years. 350 million years. The Orion Arm is a structure so large that even traveling at the fastest speeds humanity has ever achieved, you could not cross it in the time that has passed since the first vertebrates crawled out of the oceans and onto land. The first forests, the age of reptiles, the entire rise and fall of the dinosaurs, the evolution of mammals, the emergence of primates, every chapter of complex life on land, all of that would fit inside the time it takes to cross the Orion Arm at Voyager speed, and you would still not be finished. The entire stellar neighborhood we explored earlier, all 60 stars within 17 light years of the Sun, occupies a volume of space that is less than 1% of the arm's width. Less than 1%. Everything from Proxima Centauri to Sirius to Barnard's star to Wolf 359, all of it. Every star we call nearby, every target we dream of reaching someday, is crammed into a region so small relative to the Orion Arm that it would be invisible on any map drawn at the arm's true scale. You could not mark it. You could not label it. It would vanish into the line width of the arm's boundary. The solar system itself, at less than 1,000 of a light year across, is so far below the scale of the arm that comparing the two is almost meaningless. It is like comparing the width of a single atom to the width of a football field, and then realizing that the football field is itself a tiny patch on a continent. And yet the Orion Arm is not empty space with a label slapped on it. It is not just a region defined by coordinates on a galactic map. It is a physical structure filled with real, tangible, enormously complex things. Gas clouds spanning hundreds of light years. Stellar nurseries where new solar systems are being assembled right now. Supernova remnants. The expanding shells of debris from stars that exploded thousands or millions of years ago. Open star clusters. Groups of young stars born from the same molecular cloud and still drifting together through the arm. Dark nebulae. Dense curtains of dust that block the light of everything behind them. Emission nebulae glowing with the light of ionized hydrogen, excited by the radiation of nearby hot stars. Planetary nebulae. The shed outer layers of dying sun-like stars expanding into the surrounding medium. And winding through the arm like a vast skeletal backbone, a structure so large and so recently discovered that its existence came as a genuine surprise to the astronomers who found it. A wave of dense gas nearly 9,000 light years long, oscillating above and below the plane of the galaxy like a slow, cosmic serpent. The Orion Arm is not a backdrop. It is not a passive container that happens to hold stars. It is alive with activity, dense with structure, and layered with features that operate on scales so far beyond human experience that even professional astronomers have to work to hold the full picture in their minds. And every one of those features, every nebula, every star-forming region, every wave and shell and cloud is part of the structure you live inside. We are going into that structure next. We are going to walk through the interior of the Orion Arm and see what it contains. From the quiet cavity the sun currently drifts through to the colossal chain of stellar nurseries that scientists now believe may be the arm's true backbone. And every step of that journey is going to make the word local feel stranger than it already does. Now we go inside. We have established what the Orion Arm is. We know it is a spiral arm structure roughly 3,500 light years wide and at least 20,000 light years long, curving through the disk of the Milky Way between the Sagittarius and Perseus arms. We know the Sun sits on its inner rim, about halfway along its length. We know it was once dismissed as a minor spur, and has since been recognized as something far more substantial. But so far, we have talked about the arm mostly as a shape on a map, a region defined by boundaries and dimensions. That is not what the Orion Arm actually is. It is not a hollow corridor drawn on a chart. It is a living piece of galactic machinery, dense with structure, layered with features, and filled with objects so large and so violent that describing them requires a deliberate effort not to slip into language that sounds like exaggeration. Everything we are about to walk through is real, measured, and confirmed by observation. And all of it is inside the same structure you are sitting in right now. Let us start with the space immediately around the Sun, because even here, in our own tiny corner of the arm, the environment is not what most people expect. The Sun does not drift through a uniform medium of gas and dust. It sits inside a cavity, a bubble, a region of unusually low-density space surrounded on nearly all sides by denser walls of gas and molecular cloud material. This feature is called the local bubble, and understanding it is the first step toward understanding the interior architecture of the Orion Arm. The local bubble is a vast, irregularly shaped cavity in the interstellar medium, stretching roughly 1,000 light-years across in its longest dimension. Inside it, the density of gas is extraordinarily low, roughly 100 times less dense than the typical interstellar medium in this part of the galaxy. The interior is filled with hot, tenuous plasma at temperatures of roughly 1,000,000 degrees. A diffuse glow of ionized gas so thin that it would qualify as a harder vacuum than anything achievable in a laboratory on Earth. And yet, by the standards of interstellar space, this cavity is a real and significant feature. It has boundaries, it has a shape, it has a history. That history begins approximately 14 million years ago. At that time, a cluster of massive stars in a stellar association, now identified as part of the Scorpius-Centaurus Association, a group of young, hot stars located a few hundred light-years from the Sun's current position, began to die. Massive stars live fast and die violently. They burn through their hydrogen fuel in a few million years, swell into supergiants, and then collapse and explode as supernovae, each one releasing more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. Over the course of several million years, roughly 15 of these massive stars exploded in sequence, each supernova blasting a shockwave outward through the surrounding gas. Those shockwaves carved out the cavity. They swept the gas and dust outward, compressing it into the dense walls that now define the bubble's boundaries. And on those walls, in the compressed ridges of gas piled up by millions of years of supernova shockwaves, something remarkable happened. The compressed gas became dense enough to collapse under its own gravity. Stars began to form. In 2022, a team of astronomers led by Catherine Zucker at the Harvard and Smithsonian Center for Astrophysics published a landmark study in the journal Nature, demonstrating that essentially all of the star-forming regions within about 500 light-years of the Sun sit on the surface of the local bubble. Not near it, not coincidentally close to it, on it. The Taurus molecular cloud, where low-mass stars are forming right now, sits on the bubble's wall. The Ophiuchus cloud complex sits on another part of the wall. The Lupus clouds, the Chimalian clouds, the Corona Australis cloud, all of them lie on the bubble's compressed shell. The team used precise three-dimensional positions of these star-forming regions, measured using Gaia data, and showed that they all sit on the surface of a single expanding structure. The bubble is not just a void, it is an engine. Its expanding shell has been triggering star formation for millions of years, sweeping gas into dense ridges along its walls and giving birth to the very stellar nurseries that astronomers have been studying in our local neighborhood for decades. The connection had been suspected before, but the Zucker study proved it with a clarity that left little room for debate. The sun itself was not born inside the local bubble. It wandered into the cavity roughly 5 million years ago, as it orbited the galactic center, drifting through one of the bubble's thinner walls and into the low-density interior where it remains today. It is a visitor, passing through a cavity carved by stars that died long before it arrived. More recent work has refined the picture further and revealed something unexpected. In 2024, a study by Theo O'Neill and colleagues used high-resolution, three-dimensional dust maps constructed from Gaia observations to build the most detailed model yet of the local bubble's shape. What they found surprised the community. The local bubble is not actually a sealed sphere. Its northern wall, the side facing away from the galactic plane in the direction of the galactic North Pole, appears to have ruptured. The wall has burst open. Hot gas from inside the bubble is leaking out through the break, streaming upward into the galactic halo like smoke rising through a hole in a ceiling. The researchers described the local bubble not as a bubble at all, but as a local chimney, a cavity open at the top, venting its energetic contents into the vast, diffuse space above and below the concentrated disk of the galaxy. The bubble's boundaries are also more irregular than earlier models suggested, with narrow tunnels connecting it to neighboring cavities in the interstellar medium, creating a complex, interconnected network of voids, walls, and passageways threaded through this part of the Orion Arm. The interstellar medium is not a smooth, featureless gas. It is a Swiss cheese of cavities and shells, each one the product of millions of years of stellar feedback. This is the environment immediately surrounding the Sun, a 1,000 light-year cavity carved by the deaths of massive stars, walled in by compressed gas where new stars are actively being born right now, open at the top like a chimney, and connected by tunnels to neighboring cavities nearby. It is a dramatic and dynamic environment, and it is small. Relative to the Orion Arm, the local bubble is a minor feature. At roughly 1,000 light-years across, it spans less than a third of the arm's width, and less than 5% of its length. It is one pocket in a structure that contains thousands of such pockets, each one shaped by its own history of stellar birth and death, each one a chapter in the ongoing story of the arm's evolution. Step outside the local bubble and the Orion Arm reveals itself as something far larger and more structured than any single cavity or cloud. And the feature that most dramatically illustrates the arm's true internal architecture was not even discovered until 2020. It is called the Radcliffe Wave. In January of 2020, a team of astronomers led by João Alves at the University of Vienna published a discovery that surprised even seasoned galactic researchers. Using three-dimensional maps of the positions of nearby molecular clouds, constructed from precise distance measurements derived from the European Space Agency's Gaia satellite data, they identified a coherent structure of dense gas stretching approximately 8,800 light-years through the Orion Arm. It was not a random scattering of clouds. It was not a loose association of unrelated features that happened to lie in a line. It was a single, continuous, wave-shaped chain of gas and stellar nurseries, undulating above and below the midplane of the Milky Way's disk in a pattern that follows a damped, sinusoidal wave with an amplitude of roughly 500 light-years. The wave oscillates up and down relative to the galactic plane like an enormous, slow-moving ripple frozen in the gas of the arm. The Radcliffe Wave, named after the Radcliffe Institute for Advanced Study where several members of the team were based, spans approximately 40% of the Orion Arm's total length. It contains most of the major star-forming molecular cloud complexes in the solar neighborhood, including the Orion Molecular Cloud Complex, the Taurus Molecular Cloud, the Perseus Molecular Cloud, and portions of the Cygnus star-forming region. These are not small features. The Orion Molecular Cloud Complex alone stretches over several hundred light-years and contains enough gas and dust to form tens of thousands of stars. The Taurus Molecular Cloud, one of the nearest star-forming regions to the Sun at roughly 400 light-years away, is an active nursery producing low-mass stars right now. Each of these regions was already known individually. What the Radcliffe Wave revealed was that they are not isolated. They are connected. They are all part of one enormous coherent structure threaded through the arm like a spine through a body. This discovery fundamentally changed how astronomers understand star formation in our part of the galaxy. Before the Radcliffe Wave, the prevailing model for the arrangement of nearby star-forming regions was the Gould Belt, a concept dating to the 1870s when astronomer Benjamin Gould noticed that many bright young stars seemed to lie along a band tilted about 20 degrees relative to the Milky Way's disk. The Gould Belt was imagined as a ring of young stars and gas roughly 3,000 light-years across, centered not far from the Sun, tilted at an angle to the galactic plane. For more than a century, it was the standard framework for understanding why certain nearby star-forming regions appeared to trace a tilted band across the sky. Textbooks included it. Researchers referenced it. It seemed like a settled piece of local galactic geography. But the Radcliffe Wave showed that the Gould Belt was an incomplete picture, a two-dimensional projection of something far larger and more complex. The molecular clouds that had been attributed to the Gould Belt turned out to be local peaks in the three-dimensional wave structure, crests and troughs that, when viewed from Earth's specific position, happened to look like a tilted ring. The ring was an illusion created by our viewing angle. The reality was a wave nearly 3 times longer than the belt it replaced, stretching far beyond the boundaries of the old Gould Belt model in both directions along the arm. In 2024, a follow-up study led by Ralph Konitska and colleagues confirmed that the Radcliffe Wave is not a static structure. It is a traveling wave. The gas is oscillating, moving up and down relative to the galactic plane, and the entire structure is slowly drifting radially outward, away from the galactic center. This motion suggests the wave may have been set in motion by some large-scale perturbation, perhaps a collision with a satellite galaxy, a disturbance in the dark matter halo surrounding the Milky Way, or an instability at the boundary between the galactic disk and the halo. The precise origin of the wave remains an open question, but its existence is confirmed, its motion is measured, and its role as the dominant reservoir of star-forming gas in the local Milky Way is established. A team led by Swiggum and colleagues has proposed that the Radcliffe Wave constitutes the gas spine of the entire Orion Arm, the structural core along which most of the arm's star formation is concentrated. If this interpretation is correct, then the Radcliffe Wave is not just a feature within the arm. It is the arm's skeleton. the scaffold around which the rest of the arm's activity organizes itself. Think about that for a moment. A single coherent structure of gas, nearly 9,000 light-years long, oscillating through the galactic plane, containing the raw material for thousands of future star systems, threaded through the arm like a wavering vein through living tissue. And the sun is sitting right next to it, drifting along within a few hundred light-years of the wave's nearest segment. You are parked beside the spine of your own galactic arm. That is where you live. Now let us look at some of the specific structures embedded within and along the Orion Arm, because the arm is not just gas and dust. It is populated by objects that astronomers have been studying for centuries. Objects so luminous and so energetically active that they are visible across thousands of light years. The Orion Nebula is perhaps the most famous of these. We mentioned it briefly earlier, but it deserves a closer look now because it illustrates something important about the arm's interior. The Orion Nebula sits roughly 1,300 light-years from Earth. It is part of the much larger Orion Molecular Cloud Complex, a vast region of dense gas and dust stretching across several hundred light-years. The nebula itself is about 24 light-years across and contains enough mass to build roughly 2,000 stars the size of the Sun. At its heart sits the trapezium, a tight cluster of 4 massive, young, blindingly hot stars whose intense ultraviolet radiation is ionizing the surrounding gas and making the nebula glow. The trapezium stars are less than 1 million years old. In astronomical terms, they were born moments ago. The Orion Nebula is the closest region of massive star formation to Earth. When you look at it through a telescope, you are watching the process that built the Sun and the solar system roughly 4.5 billion years ago, playing out in real time, or rather, playing out as it was 1,300 years ago, since the light you are receiving left the nebula that long ago and has been traveling toward you ever since. You're watching gravity pull gas into dense knots. You're watching those knots collapse and heat up until nuclear fusion ignites in their cores and a new star is born. You're watching protoplanetary disks, flattened rings of gas and dust, orbiting newborn stars, which will eventually coalesce into planets, moons, asteroids, and comets. The James Webb Space Telescope has observed hundreds of these protoplanetary disks inside the Orion Nebula in stunning detail, revealing structures that suggest planet formation is already underway in systems that are less than 1 million years old. Some of these disks show gaps and rings in their dust distribution, features that are widely interpreted as evidence that young planets are already forming within them, sweeping up material as they orbit their infant stars. The nebula is not a relic or a monument. It is a construction site, assembling new solar systems at this very moment. And this entire region, this vast factory of new worlds, is one feature inside the Orion Arm. One nursery among many. One node on the Radcliffe Wave's long chain of star-forming complexes. Roughly 4,500 light-years from the Sun, near the far end of the Orion Arm, as seen from our position, sits a very different kind of star-forming region. This is Cygnus X, one of the most powerful and prolific stellar nurseries in the entire Milky Way. Cygnus X is not a single nebula. It is a sprawling complex of molecular clouds, hydrogen-2 regions, and young stellar associations covering an area of sky several degrees across in the constellation Cygnus. Looking towards Cygnus from Earth, you are looking along the length of the Orion Arm, peering down its barrel into one of its densest and most active stretches. Because the arm curves through the galactic disk, and our line of sight runs roughly parallel to its long axis in that direction, objects at many different distances along the arm are superimposed on the same patch of sky, creating a complex, layered vista of star formation at multiple depths. At the heart of Cygnus X is the Cygnus OB2 association, one of the most massive concentrations of young, hot, luminous stars in the galaxy. Cygnus OB2 alone contains thousands of OB-type stars, the hottest and most massive stellar class known. Each one of these stars is burning through its nuclear fuel at a furious rate, living a life measured in millions of years rather than billions, and blasting its surroundings with radiation and stellar winds powerful enough to sculpt the gas around it into pillars, bubbles, shells, and filaments visible across thousands of light years. When these stars die, they will explode as supernovae, seeding the surrounding gas with heavy elements and potentially triggering the next generation of star formation in the process. The total mass of the Cygnus X complex is estimated at several million times the mass of the Sun. It is producing stars at a rate that dwarfs the Orion Nebula, and it is inside the Orion Arm, not inside the Perseus Arm, not inside the Sagittarius Arm, inside the arm that was once dismissed as a spur. The fact that a stellar factory as massive and as productive as Cygnus X belongs to the Orion Arm is itself part of the evidence that led astronomers to reclassify the arm as a major structure. A minor spur should not contain a star-forming region of this scale. The Orion Arm does. Between the Sun and these headline features, the arm is filled with an enormous variety of other structures, each one occupying its own scale and playing its own role in the ongoing cycle of stellar birth, life, and death that defines a spiral arm. Open star clusters are scattered throughout the arm like villages along a highway. These are groups of stars born from the same molecular cloud at roughly the same time, still loosely bound by gravity, drifting together through the arm as a coherent family. The Pleiades, a cluster of hot blue stars roughly 440 light-years from Earth, visible to the naked eye as a tiny dipper-shaped grouping often called the Seven Sisters, is inside the Orion Arm. It is a young cluster, only about 100 million years old, still wrapped in wisps of the nebula it formed from. So is the Hyades cluster, about 150 light-years away, whose stars form the V-shaped face of the constellation Taurus. The Hyades is older, roughly 625 million years old, and its stars are already beginning to drift apart, gradually losing their gravitational grip on each other as encounters with other stars and molecular clouds tug at the cluster's edges. Farther away, deeper into the arm, there are clusters that most people have never heard of but that astronomers use as distance markers and tracers of the arm's structure. These clusters are young by galactic standards, typically a few 100 million years old or less, and they are direct evidence of recent star formation within the arm. Older clusters gradually disperse as gravitational interactions with passing clouds and other stars pull their members apart over hundreds of millions of years. The arm is constantly producing new clusters and slowly dissolving old ones, a perpetual cycle of stellar communities forming, living together briefly, and then scattering their members into the general population of the galactic disk. OB associations are larger, looser groupings of the most massive and luminous stars. These associations are not gravitationally bound. Their stars were born in the same molecular cloud complex, but are already drifting apart. They are important because they trace the most recent and most intense episodes of star formation. The Scorpius-Centaurus Association, the same group whose ancient supernovae carved the local bubble, is one of the nearest OB associations to the Sun. It is a reminder that the Arm's history of star formation is not just something happening far away in places like Cygnus X. It is happening right here, close to the Sun, shaping the very environment we exist in. Dark nebulae, dense clouds of gas and dust that block the light of everything behind them, are draped across the Arm in every direction. The Horsehead Nebula, that iconic silhouette of a horse's head outlined against a curtain of glowing hydrogen gas, is about 1,300 light-years away, inside the Orion Molecular Cloud Complex, inside the Orion Arm. It is a pillar of cold, dense gas, roughly 3.5 light-years tall, sculpted by the radiation of nearby hot stars that are slowly eroding its surface. Barnard's Loop, a vast semicircular arc of glowing hydrogen surrounding much of the Orion constellation, stretches roughly 300 light-years across and is part of the same complex. It is thought to be the remnant of supernova explosions that occurred within the Orion region roughly 2 million years ago, a fading echo of stellar violence still visible in ionized hydrogen across hundreds of light-years of the Arm. These structures are not decorations. They are not cosmic wallpaper. They are functional components of the Arm's ecosystem, each one playing a specific role in the cycle that transforms raw interstellar gas into stars, planets, and eventually back into gas again. Dark nebulae are the cocoons where new stars gestate, shielding the dense cores of collapsing gas from the disruptive radiation that fills the surrounding space. Emission nebulae are the region where young, hot stars have ignited and are now flooding their surroundings with ultraviolet light, ionizing the gas and making it glow. Supernova remnants are the expanding debris fields of dead massive stars, seeding the interstellar medium with heavy elements forged in the cores of their progenitors and in the cataclysmic violence of the explosion itself. Every carbon atom in your body, every oxygen atom you breathe, every calcium atom in your bones, every iron atom in your blood was forged inside a star and scattered into the interstellar medium by a supernova somewhere in this Arm or its predecessors billions of years ago. You are not merely living inside the Orion Arm. The Arm is what you are made of. Its history is written in your chemistry. And all of these structures, the local bubble, the Radcliffe Wave, the Orion Nebula, Cygnus X, the open clusters, the OB associations, the dark nebulae and emission nebulae, and supernova remnants, every one of them is spread across a volume so vast that the distances between them are measured in hundreds or thousands of light years. The Orion Nebula is over 1,000 light-years from the Sun. Cygnus X is over 4,000 light-years away. The Radcliffe Wave's nearest segment is a few hundred light-years from the Sun, but its far end is nearly 5,000 light-years away. These features are not packed together like buildings in a city. They are scattered across the Arm with enormous gulfs of comparatively empty space between them. Each one separated from the next by distances that would take our fastest spacecraft tens of millions of years to cross. This is the interior of the Orion Arm. Not an empty corridor with a name on a map. Not a quiet suburban zone of the galaxy with nothing worth noting. It is a three-dimensional landscape of staggering complexity, populated by structures that range in scale from a few light-years to nearly 9,000, threaded with a wave of star-forming gas that may be the Arm's structural backbone, and animated by a ceaseless cycle of stellar creation and destruction that has been running for billions of years and will continue for billions more. It is alive in the way that an ancient forest is alive, not because it is conscious, but because it is constantly building, burning, collapsing, and rebuilding on timescales that dwarf anything a human civilization has ever witnessed or ever will. And here is the thought that should be forming in the back of your mind as you take all of this in. Everything we have just described, every structure, every nebula, every cluster, every wave and bubble and cloud is inside the Orion Arm. Just the Orion Arm, one structure among several in the Milky Way. A structure that is roughly 3,500 light-years wide and 20,000 light-years long in a galaxy that is 100,000 light-years across. Everything we have toured, from the local bubble to Cygnus X, occupies a fraction of one feature of one galaxy. And that galaxy is one of hundreds of billions in the observable universe. The Arm contains all of this, and compared with the Milky Way as a whole, the Arm is small. That is the tension we are about to confront directly. Because the word local, the word that astronomers use casually to describe the Orion Arm and everything inside it, is about to stop making any kind of intuitive sense. And when it does, the real weight of this story will finally land. Now let us see where we actually are. We have walked through the interior of the Orion Arm. We have seen its structures, its nurseries, its wave of star-forming gas, the bubble carved by ancient supernovae in which the sun currently drifts. We have felt the scale of individual features inside it. Regions spanning hundreds or thousands of light years, complexes containing enough gas to build tens of thousands of stars, a wave nearly 9,000 light years long undulating through the arm like a slow pulse. All of it enormous, all of it inside one structure. Now we pull back one final time and place that structure inside the galaxy it belongs to. Because the Orion Arm, for all its internal complexity, for all the light years of nebulae and clouds and stellar nurseries packed within it, is not the Milky Way. It is a piece of the Milky Way. And the piece is much smaller than the whole. The Milky Way is roughly 100,000 light years in diameter. Some recent estimates place it slightly larger, perhaps 120,000 light years if you include the faintest outer extensions of the disk. But 100,000 is the commonly accepted round figure for the luminous disk. The Orion Arm is roughly 20,000 light years long. That means the arm stretches across about 1/5 of the galaxy's full width. 1/5 sounds significant, and in absolute terms it is. 20,000 light years is an almost inconceivable distance. But it means that 4/5 of the galaxy's diameter lies outside the Orion Arm entirely. The structures that fill the rest of the disk are immense. The Perseus Arm, the major arm just outward from the Orion Arm, wraps around a much larger portion of the galactic disk. The Scutum Centaurus Arm, on the opposite side of the galaxy, stretches tens of thousands of light years along its arc, curving from near the galactic center out through the far side of the disk, populated by some of the most luminous star-forming regions and the densest molecular cloud complexes in the entire Milky Way. These are the galaxy's primary structural features. The Orion Arm is a substantial feature. It is not a minor spur, but it is still smaller than the galaxy's primary arms. Shorter, narrower, less massive. It is still one chapter in a much longer and much heavier book. And the width tells a sharper story. The Orion Arm is roughly 3,500 light years wide. The Milky Way's disk is roughly 100,000 light years across. The arm's width is about 3.5% of the galaxy's diameter. If you drew the Milky Way as a circle on a sheet of paper, the Orion Arm would be a narrow, slightly curved band occupying a small arc between two larger bands. It would not dominate the drawing. It would not command the eye. It would be one of several features, recognizable if you knew where to look, but not the centerpiece. This is where you live. Not in the heart of the galaxy, not along one of its grandest arms, not in any position that would draw attention on a galactic map. You live in a medium-sized arm segment, 2/3 of the way out from the center, in a region that, by galactic standards, is neither particularly dense nor particularly empty. It is average, and even average at this scale is beyond comprehension. The Sun orbits the center of the Milky Way. This is not a metaphor. It is not a figure of speech. The Sun, along with the entire solar system, every planet, every moon, every asteroid, every comet, every grain of dust, and every spacecraft humanity has ever launched, is in continuous physical motion around the galactic center, held in orbit by the combined gravitational pull of the roughly 100 billion to 400 billion solar masses of matter contained within the galaxy. You do not feel this motion. You cannot detect it with your senses, but it is happening right now. At this moment, as you listen to this, the Sun's orbital speed is approximately 828,000 kilometers per hour. In miles, that is over 500,000 miles per hour. At that velocity, the Sun could cross the distance from the Earth to the Moon in less than half an hour. It could reach Mars in a matter of days. It is moving at a speed so far beyond ordinary human experience that calling it fast does not begin to capture what it means. The Sun is hurtling through the galaxy at over 500,000 miles per hour, and you feel absolutely nothing. And at that speed, one full orbit around the galactic center takes approximately 230 million years. Astronomers sometimes call this a galactic year, 230 million Earth years for one single lap around the Milky Way. Let that settle. The last time the Sun was at roughly this same position in its orbit, the middle of the Triassic period was underway on Earth. The first dinosaurs had barely appeared. Pangaea was still a single landmass. The Atlantic Ocean did not exist. The Rocky Mountains had not begun to form. The world was unrecognizable. That is one galactic year. One orbit. The Sun has completed roughly 20 orbits since it formed about 4.5 billion years ago. 20 laps. In the entire lifetime of the solar system, across all the eons in which the Earth formed, life appeared, evolved from single cells to fish, to reptiles, to mammals, to primates, to people. The Sun has circled the galaxy only 20 times. The galaxy is so large and the orbit so immense that even at over 500,000 miles per hour, a single trip around takes longer than the entire age of the dinosaurs, longer than the entire Cenozoic era, longer than most of the major chapters of Earth's geological history combined. And the Sun is not orbiting the edge of the galaxy. It is orbiting at a distance of roughly 26,000 light years from the center, about halfway between the core and the outer rim. The circumference of that orbit is roughly 160,000 light years. The Sun covers that distance in 230 million years because it is moving at over 500,000 miles per hour, continuously, without pause, for 230 million years. That is the scale of the galaxy in which the Orion Arm sits. The arm is one piece of a disk so large that even traveling at interplanetary speeds, circling it once takes 250 million years. Now, consider what this means for any attempt to explore even the Orion Arm, let alone the rest of the galaxy. We have already established that reaching the nearest star, Proxima Centauri, at 4.24 light-years is beyond current human technology on any practical timescale. But let us imagine something more ambitious. Let us imagine that someday, perhaps centuries or millennia from now, humanity develops the ability to travel at the speed of light itself. Pure fantasy by current physics, since nothing with mass can reach light speed, but grant it for the sake of the thought experiment. How long would it take to cross the Orion Arm at light speed? The arm is 3,500 light-years wide. At light speed, crossing it from one side to the other would take 3,500 years. Not 3,500 days. Not 3,500 months. 3,500 years. That is a span of time longer than the gap between the fall of ancient Troy and the world you live in today. If a beam of light had been fired from the inner edge of the Orion Arm at the moment the ancient Greeks were laying siege to the city of Troy, that beam would still not have reached the outer edge. It would still be in transit, still crossing the arm, with nearly 300 light-years left to travel before completing a journey that began before the Western alphabet existed, at the speed of light, the fastest speed the universe allows. The arm is 20,000 light-years long. At light speed, traversing it end to end would take 20,000 years. 20,000 years is roughly the time since the end of the last glacial maximum, the peak of the last ice age, when massive ice sheets covered much of North America and Northern Europe and sea levels were over 400 feet lower than they are today. The entire span of human civilization, every city built, every language spoken, every war fought, every work of art created, every scientific discovery made, from the first permanent agricultural settlements in Mesopotamia to the device you are using right now, all of it fits inside the time it would take light to travel from one end of the Orion Arm to the other. Everything humanity has accomplished would be consumed by one light-speed journey along the length of the arm. And the Milky Way is 100,000 light-years across. Even at light speed, crossing the full galaxy would take 100,000 years. Humanity as a species, Homo sapiens, has existed for roughly 300,000 years. A light-speed crossing of the Milky Way would consume a third of the total time that modern humans have walked the Earth. And light speed is not achievable. It is a theoretical ceiling that cannot be reached by anything with mass. Any real journey would be slower, far slower, and the distances do not shrink to accommodate human limitations or human hopes. This is the reality that the Orion Arm forces you to confront. Not the abstract vastness of the universe, not the incomprehensible scale of the observable cosmos at 93 billion light-years across, but the specific, concrete, measurable vastness of the structure you are inside right now. The structure that contains your sun, your planet, your nearest stars, your most familiar constellations. The structure that astronomers call local. That word, local, is doing work it was never designed to do. In everyday life, local means nearby, reachable, part of your immediate environment, the local grocery store, the local park, the local neighborhood. You can walk to local things, you can drive to them in minutes. Local implies accessibility. It implies a human-scale relationship between you and the thing being described. In galactic astronomy, local means the Orion Arm, a structure 3,500 light-years wide and 20,000 light-years long, containing millions of stars, thousands of nebulae, a wave of gas nearly 9,000 light-years long, star-forming regions producing new solar systems at this very moment. Supernova remnants seeding the interstellar medium with heavy elements. Open clusters drifting apart over hundreds of millions of years. And enough raw material to build billions of worlds that have not yet been imagined. This is what astronomers mean when they say local. And the dissonance between the everyday meaning and the astronomical meaning is not a quirk of language. It is not a cute contradiction to notice and then move past. It is the core of what makes the Orion Arm so deeply unsettling to think about clearly. Because local should not be this big. Local should not contain distances that light itself takes millennia to cross. Local should not be a place where the nearest exit, the gap between the Orion Arm and the next spiral arm over, is measured in thousands of light years of empty galactic disk. But it is. The nearest major arm outward from the sun's position is the Perseus Arm. The gap between the inner edge of the Perseus Arm and the outer edge of the Orion Arm is roughly 6,500 light years of interarm space. 6,500 light years of comparatively empty galactic disk, thinner in stars and gas than the arms on either side, a no man's land between galactic structures, stretching across a distance that light needs more than 6 millennia to traverse. To leave the Orion Arm and enter the Perseus Arm, even at light speed, would take longer than all of recorded human history. Longer than the span from the invention of writing to the present day. Longer than the rise and fall of every civilization whose name you have ever heard. The entire human record, compressed into a beam of light, would not reach the next arm over. At Voyager's speed, the crossing would take roughly 115 million years. 115 million years ago, the middle of the Cretaceous period, dinosaurs still dominated the Earth. Flowering plants were just beginning to spread. The asteroid that would end the age of reptiles was still 50 million years in the future. The interarm gap between us and the nearest neighbouring arm spans a travel time longer than the entire age of mammals. And even this comparison understates the isolation because it assumes you have already crossed the Orion Arm itself to reach its outer edge. You have not. You are not at the edge. You are in the middle, on the inner rim, surrounded by thousands of light years of your own arm in every direction before you even reach the boundary where the interarm gap begins. And that is just the gap to the next arm. The Perseus Arm itself is another vast structure, longer and broader than the Orion Arm, with its own nebulae, its own star-forming regions, its own molecular clouds and stellar associations. Beyond Perseus lies more interarm space, then the outer edge of the galactic disk, then the halo, then the intergalactic void. Inward from the Orion Arm lies the Sagittarius Carina Arm, then more interarm space, then the denser inner regions of the galaxy, then the bar, then the core, then Sagittarius A star, the supermassive black hole at the center of it all, 26,000 light years from where you are sitting. Every direction you look, from the Orion Arm outward to the edge of the galaxy or inward to its heart, the distances are measured in thousands or tens of thousands of light years. The Orion Arm is not a stepping stone to the rest of the Milky Way. It is a prison, in the gentlest and most honest sense of that word. Not a prison of walls and bars, but a prison of distance, of physics, of the simple, inarguable fact that the speed of light is finite, that human life is short, and that the structures we live inside are built on scales that do not recognize human existence as relevant. before humanity can dream of crossing the Milky Way, of sending ships or probes or signals to the far side of the galaxy, it would first have to face the scale of its own neighborhood. And its own neighborhood is already too large. The Orion Arm contains everything we have ever seen in the night sky. It contains every star we have ever named, every nebula we have ever photographed, without first sending a spacecraft beyond the solar system, every world we have ever imagined visiting, every point of light that has ever inspired a poem or a prayer or a scientific career. It contains the Orion Nebula and the Cygnus X complex, and the Radcliffe Wave and the local bubble and Proxima Centauri and Sirius and Betelgeuse and the Pleiades and the Horsehead Nebula and Barnard's Loop and every other object that has ever sparked a human being's curiosity about what lies beyond the Earth. All of it. Every single one. Inside one arm. And it is one arm. One single segment of spiral structure. One curved band of stars and gas in a galaxy that contains several such bands. Most of them larger, all of them farther away. All of them separated from us by gulfs of empty galactic space that make the distance to the nearest star look like a single step across a room. This is the truth that the Orion Arm reveals when you look at it clearly. It is not the largest structure in the universe. It is not even the largest structure in the galaxy. It is mind-breaking for a simpler and more personal reason. It is mind-breaking because it is local, because you are inside it, because everything you have ever known is inside it, and because even this one local structure, this one galactic neighborhood, this one arm among several, is so vast that the entire history and reach of human civilization occupies a point within it that is too small to mark on any map drawn at the arm's true scale. Every human being who has ever lived has lived inside the Orion Arm. Every human being who will ever live, for as far into the future as it is reasonable or even optimistic to project, will live inside it too. Not one of us has ever traveled more than a vanishingly tiny fraction of 1% of its length. The farthest any human-made object has traveled, Voyager 1, after nearly 50 years of continuous flight at 38,000 miles per hour, has covered a distance equal to roughly 1/10,000,000th of the arm's length. Write that as a percentage, and you get a number so close to zero that it takes 4 decimal places of zeros before the first meaningful digit even appears. It is so small, it is effectively indistinguishable from zero. In nearly half a century of flight, the fastest object humanity has ever launched has traversed an amount of the Orion Arm that rounds to nothing. We have not moved. We have not explored the arm. We have not even begun to cross the threshold of the structure we call home. And at Voyager's speed, we never will. And yet, the Orion Arm is home. It is where the sun formed, roughly 4.5 billion years ago, from a collapsing cloud of gas and dust, enriched by the deaths of earlier generations of stars, somewhere in this arm or a structure that preceded it. It is where every atom in your body was originally assembled, cycled through multiple generations of stars and supernovae and interstellar clouds over billions of years of patient galactic chemistry before ending up, against all reasonable probability, in the particular arrangement that is you. Sitting here, listening to this, thinking about the scale of the place you live. The arm built you, not deliberately, not with purpose or intent, but through the blind, patient, enormously powerful processes of gravity, nuclear fusion, stellar death, and time, operating across a structure 3,500 light-years wide for billions of years without pause. You are a product of the Orion Arm in the same way that a coral polyp is a product of the ocean. The ocean does not know the polyp exists. The polyp cannot comprehend the ocean. But the polyp is made of the ocean's materials, shaped by the ocean's currents, fed by the ocean's chemistry, and will return to the ocean's substrate when it dies. You are the same relative to the arm, made of its gas, shaped by its stars, fed by its chemistry, briefly aware of where you are and what you are part of, and then gone while the arm continues without noticing. There is something in this realization that goes beyond the simple shock of large numbers. It is not just that the Orion Arm is big, it is that the word local, the most domesticated and comfortable word in our spatial vocabulary, turns out to refer to something that exceeds human comprehension entirely. We use local to mean close, familiar, manageable, ours, and in galactic astronomy, it means a structure that light takes 20,000 years to traverse, that contains millions of stars, that has been building and destroying solar systems for billions of years, and that will continue doing so for billions more after the sun burns out and the Earth is gone and every trace of human civilization has been recycled into the interstellar medium of the arm. Local means all of that, and the fact that it means all of that, and that we still use the word with a straight face, is perhaps the most honest measure of the gap between what we are and where we are. The Orion Arm does not care that you are inside it. It is not aware of you. It has no center of awareness, no purpose, no direction, no plan. It is a physical structure, governed by gravity and gas dynamics and nuclear physics, operating on timescales so long that the entire history of life on Earth is a brief flicker in its ongoing evolution. It was here before the sun formed. It will be here after the sun dies. And in all the billions of years between, across all the countless stars and worlds that have formed and dissolved within it, the Orion Arm has never once, to our knowledge, produced anything capable of looking at itself and understanding what it is, except possibly here, possibly now, possibly you. You are a temporary arrangement of the arm's own matter that has become, briefly, aware of the arm. You are the Orion Arm looking at itself. Not through a telescope, not through a satellite, but through the improbable fact of consciousness arising from chemistry, arising from stellar nucleosynthesis, arising from the collapse of gas clouds inside this one spiral arm structure of this one galaxy. You are the arm's way of knowing it exists. And the knowledge you hold right now about the scale and structure and contents of the Orion Arm is something that may never have existed before in the arm's entire history, and may never exist again after your species is gone. That is not a comfortable thought. It is not meant to be comfortable. The Orion Arm does not offer comfort. It offers scale. And scale, when you look at it clearly and without flinching, does something very specific to the human sense of self. It does not destroy it. It does not diminish it. It reframes it entirely. You are not small because the Orion Arm is large. You are not insignificant because the distances are beyond your reach. You are rare. You are an anomaly. You are a point of awareness in a structure that is almost entirely unaware. And the fact that you can sit here and hold the shape of the Orion Arm in your mind, can trace its dimensions and name its features, and feel the weight of its scale pressing against the edges of your comprehension, that is not nothing. That may be the single most extraordinary thing the arm has ever produced. The Orion Arm is everything we have described tonight, and vastly more than we have had time to name. It is your galactic home, your local arm, the place where everything you have ever known or loved or feared or wondered about exists. It is filled with structure, layered with complexity, animated by a cycle of creation and destruction that has been running since long before the sun was born, and will continue running for billions of years after the sun burns out and the Earth and everything on it has been returned to the interstellar medium. And it is so large that even calling it local feels like an act of breathtaking, almost absurd understatement. But it is local. It is home. And you are inside it right now. A flicker of awareness in a river of stars, briefly awake, briefly looking around, briefly understanding where you are before the current carries you on. That is what the true scale of the Orion Arm does to a mind that is willing to hold it. It does not break you with the largest number or the farthest distance. It breaks you with the realization that the largest number and the farthest distance you need to reckon with are not out there somewhere, in the deep universe, in the space between galaxy clusters, in the incomprehensible void between superclusters. They are right here. They are local. They are the dimensions of the structure you were born inside, the structure you will die inside, the structure that built you from its own materials and will reclaim those materials when you are done. The Orion Arm will melt your mind, not because it is the largest thing in the universe, not because it confronts you with numbers too big to process, though it does that too. It will melt your mind because it is the smallest thing that already exceeds your ability to grasp. It is the floor of cosmic scale, the entry level of galactic vastness, the ground floor of a building that stretches upward through the Milky Way and outward through hundreds of billions of galaxies to the edge of the observable universe and whatever lies beyond. And you cannot even reach the first floor above you. You are standing on the ground floor. You have always been standing on it, and looking up for the first time with clear eyes, you can see just enough to know that the building has no ceiling you will ever touch. Good night.